Our mission is to prepare the next generation innovators, leaders, and change agents. Welcome to the 32nd Global Teamwork event. My name is Renate Fruchter, and I'm the founding director of the PBL Lab at Stanford University, home of the AEC Global Teamwork, and host of this annual event. What is unique about our AEC Global Teamwork is that it brings together students, faculty, and industry mentors coming from 5 disciplines: architecture, structural and mechanical engineering, construction management, and lifecycle financial management. Students learn to collaborate in globally distributed teams across discipline, time, space, and culture to virtually design and build university buildings, addressing local conditions. But before we dive into the team presentations, I want to express our gratitude to all our university partners for their support and active engagement over the years. A big thank you to all our industry mentors and alumni who generously dedicate their time, attention, and knowledge to all our students to create a real-world project-based learning experience. Special thanks to our Stanford Center for Integrated Facility Engineering, Seismic, and to our industry partners, DPR Construction, Swinnerton, and HOK, for their continued support and sponsorship. A big shout out goes to our PBL Lab visionary technology sponsors for their generous support that enables us to reimagine collaboration, education, and new ways of working. Integrate data, models, and disciplines, and embed AR, VR, generative design, and optimization in the daily work practices of our students as they develop end-to-end integrated, intelligent design, manufacturing, construction workflows. So our students are invited every year to design buildings for people, questioning what is the future of learning and work. As we shape our buildings, thereafter they shape us. And lately, as we shape our technologies, thereafter they shape us. Addressing in their projects the current climate emergency, coined Code Red for Humanity by the UN Secretary General, as well as reflect in their projects our AEC industry's responsibility to adopt innovative construction 4.0 processes, digitalization, industrialization, prefabrication, and new materials to build more sustainable buildings for current and future generations. So, to address these challenges, students responded to this year's theme, Generative Minds for a Better World. AI, enhanced collaboration, and high-performance buildings. These were supported by 3 specific competition topics. The 90s Sustainability Challenge focused on time and urgency to define their sustainability impact in a temporal dimension. IPD Challenge focused on cultivating a team mindset in support of productivity in the age of construction 4.0, coined T-Mind. And last but not least, the Technology Challenge, inviting the students to connect the dots between innovative technologies, processes, and the buildings that people actually go to work and learn, focusing on sustainable, intelligent supply chain. So this year, we gathered at this annual PBL event to listen to the 3 AEC Global student teams share their projects and team process, and discuss with industry mentors their solutions. So, without any further delay, Pacific team, the floor is yours.
Okay. In this presentation, we will show you our approach at redefinition, not an update or an incremental improvement, instead, a complete shift in how we think about learning spaces. It all starts with the user, not the classroom, not the curriculum, the learner who is at the center of it all. Because the future doesn't stand still, what we build today must shift, grow, and evolve, just like the minds it's made for. What we create shouldn't just be smart. Intelligence must be embedded in every part of the product and process.
Education has come a long way, from rigid classrooms and blackboards to today's blend of screens, apps, and agile methods, still evolving, but often disconnected. Now the future, it's intelligent, seamless, and built around the learner. We're Team Pacific, and today we're going to present iLearn. My name is Lillian, and I'm a structural engineer from the Technical University of Denmark.
My name is Alexandra. I'm an architect, and I'm from Warsaw University of Technology.
My name is Claudius. I'm MEP. I'm from Silesian University of Technology.
My name is Julian. I'm the LCFM, and I'm from the Bauhaus University in Germany.
My name is Shun. I'm structural engineer from Stanford University.
Hi, I'm He Long. I'm also a structural engineer from Stanford University.
I'm Anya, and I'm construction manager, and I'm also from Stanford University.
I'm Emilio. I'm a construction manager from TU Delft.
These are our owners. Now, before digging into our project, we want to start by talking about our team process and goals, and then we will move on to our product and the sustainability and finances behind it before finishing off with a summary of our challenges.
Our journey began with the kickoff. As we moved into weeks 1 and 2, our overall performance wasn't strong. But we have a resilient team mindset and always focused on finding solutions. The week 4 critique was a turning point. We realized that although we were collaborating, we were still working in silos. After that, we committed to holding ourselves to higher standards. We started identifying inefficiencies in our team process and focused on crafting effective solutions. With this dedication, we began developing intelligent blueprints and structured decision matrix. Throughout the process, our CM Emilio created the Pacific AI agent system, which significantly boosted our productivity. After we determined our big idea, our initial solution turned out to be ineffective. Nevertheless, guided by our team mindset and the support of our AI agent system, countless great ideas emerged during our now efficient meetings. In the following weeks, we kept optimizing our solution again and again, integrating those brilliant ideas. The journey was tough and exhausting, but we never backed down. We always hold each other's back like we were one. And now, as we approach the end, it's our showtime.
Since the beginning of the project, we have a fixed team meeting once a week, and we usually wrap up with a blueprint to guide the week ahead. We also have many subgroup meetings through the week. At first, they were separated into designers, planners, and finance meetings. However, as the project grew more complex, our collaboration evolved accordingly. We began forming mixed discipline subgroups, beginning different perspectives together to tackle key decisions. We also created dedicated challenging group for our 3 challenges. The graph shows how our subgroup meetings grew, not just in number, but in diversity, reflecting how our team become more integrated, aligned, and efficient. To communicate with each other, we use WhatsApp, Discord, Zoom, and Meeting VR. And we collaborate in Miro, where we share ideas and do collaborative sketching with different disciplines. We model together in Revit and BIM 360. And we also do team cache detection in Ares VR every time we make a big change in the design. For coordination, we use Google Drive for file sharing and organization. Nayeli for pool planning session, hold approximately once a week, and Google Calendar to view each other's availability. For our team, VR wasn't just a tool, it was a turning point. Our VR session became a space where we could be playful, break down barriers, and build trust. We had many unserious and serious meetings where fun sparked creativity, encouraged bold ideas, and ultimately made our design better. At the same time, VR gave us shared spatial understanding. We weren't looking at disconnected screens, but we were inside the building together, catching issues early, testing ideas at full scale, and making decisions with clarity. VR didn't just help us see the project, it helped us see it as a team.
Now we come to our project goals, which are the key intentions that guided our approach right from the start. So first, we want to reduce resource use and meet the sustainable target values across all relevant categories. And we aim to create a flexible and future adaptable building ready for changing needs and digital systems. We also want to minimize our site footprint and maximize prefabrication to streamline the building process. And we intend to design a building that keeps operating costs low and remains resilient over time. And finally, we aim to deliver a space that supports well-being, daylight access, and intuitive, inclusive use.
Our challenges intersect in different ways, but at the center, they come together in a unified approach that is collaborative, tech-powered, and built for a long-term impact.
For the IPD challenge, what is really holding our team back? In interdisciplinary projects, teams always face challenges that slow them down. Silos, delays, and poor coordination often block the path to smarter solutions. We have identified 4 major challenges that affect our team progress. To overcome them, we have set clear goals with well-designed approaches. Taking silos as an example, at the beginning, we were working in silos. Each discipline focused on their own tasks with few communication and collaboration. We didn't really know what others were doing. As a result, we ended up with ineffective solutions. So to tackle these challenges, we have defined 4 key goals that guide our approaches. The first one is interdisciplinary collaboration, making sure that all of the disciplines are actively involved. Then we have asynchronous coordination so that even when team members aren't working at the same time, we are still aligned through a shared plan. We are also focusing on visibility of cross-disciplinary progress so that everyone understands where others are and what's coming next. And finally, we are aiming for streamlined communication and decision-making, reducing delays with AI-assisted quantity takeoffs, cost estimates, and TVD checks.
To create a sustainable, intelligent supply chain, we want to address a core issue, which is waste. Not just in terms of materials, but wasted time, effort, and knowledge. We've identified 3 key contributors to this waste: suppliers lacking up-to-date information, lack of means to track waste, and loss of information after projects. To tackle this, we've set 4 clear goals. First, to reduce rework by improving the accuracy and flow of information. Second, to actively manage construction waste through smarter tracking. And last, to minimize the site footprint with better coordination and logistics. Ultimately, we want to educate the next generation of construction managers through exposure to intelligent systems that support sustainable practice. Our method is to collect, process, and integrate information, then deliver it to the people who need it when they need it.
For sustainability challenge, the clock is ticking, and that ticking sound is a reminder time is moving forward, and with it, the climate change. We can't stop time, but we can respond. And the response starts with the decisions we make today. The buildings we design now will shape our environment for decades, from the first day of the construction to the very end of their life. Our approach is guided by 4K principles: biodiversity, resources, CO2 reduction, and human well-being. With this as our compass, we aim to create building that is not only environmentally responsible, but uplifting, healthy for the people who use them. And for our site context, our site is located in San Francisco, California. And the site has a winter season from October to April and summer season from May to September, with fog present year-round. More importantly, we face major environmental challenges, such as a 72% chance of a strong earthquake in the next 30 years, frequent droughts 60% of the time over the past 25 years, and worsening air quality due to the wildfire smoke.
Marked with red line is our site. It is a part of San Francisco State University, located in the north just by Lake Merced, surrounded with university campus and neighboring sport facilities. There is also a level difference of 15 feet between the northern and southern roads bordering the plot. The positioning of the building on our site was carefully chosen based on existing conditions, including both climate and topography. This placement creates a comfortable courtyard space for users and allows for dual access, a main entrance from Winston Drive and a secondary entrance from N State Drive and the adjacent parking area.
The big idea you will see today didn't appear out of nowhere. We started with two different concepts, each with two different structural systems. We evaluated each of these alternatives to understand their performance in 11 different sub-criteria, and you are about to see the evolution of the one that narrowly beat the rest.
iLearn is more than just a name. It's a mindset. Every I behind it reflects what this building is built for. But all of this boils down to three core ideas that shape iLearn from the ground up. User-centered design, because the people in the building shape how it works and not the other way around. Flexibility for the future, to create a structure that evolves with learning methods and not expires with them. And embedded intelligence, where technology isn't an add-on, but it's part of the system. Our starting point was a moment of redefinition. When we thought about that word, the launch of the iPhone in 2007 came to our minds, not just for its technology, but for how it changed behavior. The idea of putting users first and embracing adaptability is what inspired us to create iLearn.
We began exploring a double diamond footprint using sketches and focused deeply on user needs. Soon after, we presented our initial design and spent the following weeks developing it through cross-disciplinary collaboration. During the winter presentation, we committed to the iLearn concept. However, we felt the design didn't yet reflect the full potential of its name, so we undertook a complete redefinition, rethinking every element. And today, we're proud to present the true iLearn building. We decided to indicate our crucial design values for the university building that reflects the iLearn big idea: interaction, collaboration, and creativity are the three assets that function together to increase the potential of its users, complementing each other and creating a space conducive to the development of users, the human relations, and their well-being. The iLearn building is designed with focus on simplicity and clarity, featuring glazed facades and smooth neutral cladding. Its open character is emphasized through a structural layout that enables adaptable spaces and spacious interiors, promoting flexibility of use. We begin with the ground floor, which is designed to encourage interaction and connectivity. It offers comfortable leisure areas, creating an inviting environment for users to relax, socialize, and collaborate.
The specified load is the dive load provided from the table in AEC 7. From perspective of structural efficiency, we collaborate with architecture to put higher dive load area around the columns. The red rectangular box point out the location of retaining walls, which are covered around the excavation slope in both big classroom and auditorium. The image at right is the location of retaining walls in the context of the site.
We enter the first level from the courtyard, stepping directly into the heart of the building, a vibrant social hub centered around the main staircase, with a designated sitting area that encourages student collaboration. Straight ahead, there is a large glazed classroom with sloped seating and a cafe just nearby. As we move past the social area, we pass by the elevator on the left, and we move to the auditorium, designed with a curved audience layout and 4 exits to ensure smooth circulation and safety during emergencies.
The auditorium has a specific structure and performance needs. By using displacement ventilation, we ensure the best possible condition for users, making the space perfectly suited for its purpose.
Entering the second floor is designed to foster collaboration, offering diverse spaces and flexible learning environments that support the future of education.
For the second and third floor, we put regions with low node like classroom and office around the cantilever part, which can help reduce overall element size.
Entering the second floor from the higher northern street, we arrive in a welcoming lunch area that connects to the collaborative spaces. To the left, there are classrooms, and as we move past, we reach the top of the main staircase. We're greeted by natural light and open views. Turning right, we reach the AI pods area, personalized spaces supporting individual learning.
Inspired by modular meeting rooms, our AI pods offer pockets of privacy in a collaborative environment and come equipped with AI-driven screens and assistive touch. Whether it's a foreign student looking to learn in their native language or someone diving deep into a discipline-specific topic, the AI delivers tailored content in real time. And with ambient lighting and customizable sound, it's not just smart, it's an experience. Personalized, private, and intuitive. You never want to leave.
Continuing our journey on the second floor, we pass the fully glazed staircase offering views across the building. We then arrive at the bright central atrium, where collaborative spaces open up to the right. Moving forward, we reach the second classroom, designed to reach various learning goals. Focusing on the flexibility of our spaces, we designed the classroom that can be adjusted to the user needs by changing its arrangement. One spacious classroom can be divided into the two smaller ones or into 4 seminar rooms. All spaces allow for comfortable use due to the glazed partitions providing the natural lighting, as well as separate entrances for all of the segments. By providing movable spaces, we allow users to decide on the organization of the educational building, basing on their current needs and learning goals. Adaptability provides comfort which might be disturbed by noisy surrounding. To address this issue, we selected materials with excellent sound-reducing properties, acoustic glass for the glazed partitions, and MDF panels for soundproof ceilings. Ease of maintenance was another priority, leading us to choose high-performance wall paint that allows for bright, easy-to-clean surfaces. The color palette creates a cozy, calming atmosphere, serving as a perfect backdrop to a university life. The third floor supports creativity with fully equipped project rooms, as well as offices in the opposite part of the building that aren't tied up to any specific user group and can be adapted to changing needs. We pass by the AR-RP rooms, spaces designed to bring student vision and creativity to life. Walking along the central atrium, we arrive at the offices, located along the eastern and southern wall. As we move forward and turn left, we return to the atrium, once again immersed in the natural light streaming through the large skylight above, and we finish our trip in one of our offices. We rebranded our instructional labs as augmented reality rapid prototyping rooms to highlight the importance of creativity, innovation, and future-focused learning. The space is designed to support every stage of development. It begins with an area for brainstorming and sketching, followed by stations for digital prototyping, and at the center, a dedicated zone equipped for augmented reality.
These rooms also require a special ventilation approach, so we use operable windows, air exchange rates, and HEPA filters to ensure excellent air quality there.
And now that we've covered everything inside the building, we move to our final floor, the rooftop. Even though we designed a highly technical, smart building, we still wanted to create a space that reconnects people with nature, sort of a green oasis in the middle of the city. Therefore, the rooftop is divided into several areas. One is the community garden, where fruits and vegetables can be grown together. Another is the biodiversity zone, with insect hotels and native plants, what is helping us to strengthen and restore the local ecosystem.
We also created a social area where students and faculty can relax, meet, or even host a small events, turning the roof into a welcoming and engaging space. Right next to it, we integrated hydro panels, which extract clean drinking water directly from air using the solar energy, showcasing smart technology that provides a sustainable source of fresh water. This combination of spaces on the roof supports both environmental and social sustainability, making the roof a vibrant, functional, and nature-friendly extension of the building.
The community garden is not just a space for endorsing biodiversity, but a space for busy engineering students to come together in an outdoor community building space. By taking advantage of San Francisco's mild year-round climate, we're planting seasonal fruits and vegetables to create a roof-to-cafe system, serving the produce in-house and also generating a revenue potential of $15,000 per annum. Our LCFM does love that.
As user-centered design is one of our main goals, we aim for providing smooth circulation throughout the building. Unfortunately, some problems did still appear. First issue emerged in the corridor running between the auditorium and the entrance from the courtyard. It seems to be too narrow in case of the emergency. Luckily, we managed to analyze the issue by running the simulation in the fusor, and it came out that the space is wide enough in case of an emergency situation. Next problem was noticed in the corridors leading to the corner seminar rooms that are created when the movable partitions are closed. But also in this case, Fusor allowed us to simulate a problematic situation and make sure we provide a comfortable space for moving around. We designed our north and south facade with large glazings, which provides the light provides the lights and creates a seamless transition between the building's exterior and interior, enhancing the overall experience of openness and flow.
Glass buildings are a visual statement. They are truly stunning and gives users a unique sense of openness, connection to the outside, and natural light. But they also come with the challenges, like solar heat gains and the risk of the glare. To make our building comfortable and usable, we implemented a daylight control system combining low emission glass, which reduces incoming light and heat, with external shading that limits direct sunlight.
And with that much glass, it was clear that we needed external shading. So we ran a trade-off analysis between two facade options, a kinetic system and vertical shading fins. We ultimately choose the vertical shading fins because they come with lower and more predictable costs, they have a long lifespan, and they're corrosion resistant, which is especially important in San Francisco's foggy climate. Overall, they turned out to be the most cost-efficient and robust solution.
All of our facades show joint efforts of architect, MEP, and LCFM in providing aesthetic look, as well as at the same time user comfort.
And with such a large glass surface, cleaning costs became a major consideration for us. That's why we developed a fully automated system using cleaning robots, both for floors and facades. On top of that, we equipped our windows with a self-cleaning coating. Altogether, the setup allowed us to reduce the cleaning costs by up to 60% compared to the traditional methods.
Direct sunlight turned out to be a more complex problem than expected. So in addition to our previously mentioned shading strategies, we also added shading elements in the atrium. In the end, we created a space that feels open and welcoming while adapting to the natural circadian rhythm, with natural lighting that changes color based on the outdoor conditions, working with the rhythm of the people inside. We designed a local ventilation system for the corridors using openable windows in the central atrium, which operates based on the stack effect to drive vertical airflow. Large HVLS fans support air movement throughout the building, while makerspaces are operated additionally by cross-ventilation. System is controlled by sensors that determine when the natural ventilation is effective. This ensures energy usage reduction and improvement of user comfort. Continuing with the fan strategy, we also use ceiling fans to reduce cooling energy use by 33%, while improving the comfort of users inside. And by combining the previously mentioned elements, we developed a hybrid ventilation system based on a VAV setup with a air landing units equipped with the heat recovery and integrated air source heat pumps, providing both heating and cooling. And to ensure high indoor air quality, the system is also equipped with HEPA filters. This solution balances energy efficiency, comfort, and the health. And the ventilation system was designed to adapt to flexible classroom layouts, ensuring comfort regardless of the interior changes. We also provided targeted airflow to the areas with the AI pods, and by dividing the system into 2 zones, we reduced the duct sizes without interfering with the structural design.
Here we see the structural floor plans where we're using wide flange beams and columns. In the east and west side of the building, we have vertical circulation, which is where we have these 14 by 90 wide flange columns that serve as the fixed part of the building. To support adaptability of the rest of the floor plan, we have designed a large modular structural grid of 38 feet, which gives us maximum flexibility for different layouts and uses. And to support adaptability, we have also made sure to use same element sizes across all floors. And here we see the structure of the roof, which is consistent with the other floors. However, we have some additional beams which support our atrium and 2 big fans. In terms of gravity load path, the loads are transferred from each floor to girders and through the columns down to the foundation and the ground. Now, through collaboration with the team, we decided to use steel as our frame material so that we could have these long spans that give us openness and adaptability with small cantilevers. And steel was also a good choice for us in terms of prefabrication and the construction schedule. And its high strength to weight ratio also meant that we could work with slimmer sections, leaving good space for MEP and architecture. So we were able to achieve a comfortable floor to ceiling height of 11 feet 2 inches, with MEP being 1 foot 4 and the structure being 2 foot 6.
And now, to make all of these intangible aspects of comfort and well-being that our design team worked hard on measurable, we decided to go for the WELL certification. It captures the impact of features like our circulation-friendly layout, fresh air systems, daylight optimization, and even the urban farming. These contribute to a better health, higher user satisfaction, and ultimately add value to our building.
So here are the lateral load demands that we calculated, and they are huge numbers. So for someone who might not be familiar with the unit of kips, just to imagine like 1 Tesla weighs around 5 kips. So it's going to be a lot of Teslas. So the seismic force will be transferred from diaphragms to the frame and induce moments in beams and columns. So here's our iShake moment resistant frame. As Lillian mentioned, we want to achieve openness and adaptability. So steel moment resistant frame will be the top choice for our lateral system without any bracings. However, we found out that the demand is so big that the iShake is not able to hold it. So at this point, we discussed with LCFM and CM to make sure that our budget and the schedule allow us to implement base isolators. So by setting a target period of vibration of 2 seconds, we designed the lead rubber base isolators for iLearn building with 20 inches diameter and height and the 3.5 inches diameter lead core. So with the base isolators, now we can get rid of a lot of Teslas.
Here's our foundation system. We use big concrete rectangular footings on the large columns and smaller footings on the small columns, which were set around 2 cores. All foundation beams are 16 times 18 inches concrete rectangular beams. Using bolted web-to-web flange for beam-to-beam connections can reduce field welding, which can reduce labor costs and communication due to weather or access. For designing the network system, we actively collaborate with architects, CM, and LCFM. From perspective of architect, there is no briefing for the network system which can provide the maximum opening for the facade and opening design, which align with our big idea. For CM, the dual fuse frame can simply fabrication and erection to achieve shorter construction period. For LCFM, the dual fuse frame can reduce cost by using less steel and simplify erection process. After the earthquake, the seismic force only make fuse yielding without cost for repairing beams and columns during the life cycle. Here's first three modes of response of the structural system, which are translation in x-axis and y-axis respectively for first mode and torsion for the third mode. This is a good sign for a well-balanced network force resisting system. The maximum inter-storage drift ratio is about 1.5%, which is smaller than the requirement of 2% specified in the code. Both measurements shows the effectiveness of the design network system of the building.
Now let's see how we developed our own disruptive AI solutions to fulfill the approach for our team mindset. Having identified design feedback latency and lack of understandability created by the silos, we created a multi-agent system to handle quantity takeoffs, cost estimation, and target checking. With insights from the team about our information needs and requirements, we broke down the process into smaller tasks that single agents can handle by coordinating with each other. These agents were given a variety of tools and capabilities to fulfill their role in the system, including data processing tools, information retrieval abilities, and memory management. For example, one step in the cost estimation process is scanning for new items that haven't been seen in previous design iterations and matching them to items from a cost database built with RS means. Beyond just a tool for automation, this system is flexible, can self-correct when running into errors, and makes the workflow very explainable to other disciplines not acquainted with these processes. Just to show a demo of what we're working with, we first make a request to the system using natural language. For example, we can say, hey, could you please perform a quantity takeoff cost estimation and check the targets for the latest BIM models? Following this, the system will process these files to produce quantity takeoffs, cost estimates in an observable way, where we can verify and check their work. Here, we can become checkers rather than doers, and the whole process becomes understandable and accessible to all disciplines. Then the fun part is when the agents open up the PBL Lab's TVD tool in Excel to store and evaluate our latest results, where we can double check their work, see how we're doing on targets, and make quick design decisions. The entire process becomes so quick that we can give analysis to the design options on demand. This gives our design team confidence to explore more creative ideas, fully being aware of the impact of design decisions.
The system has already helped us a lot in making the tracking of target values and new iterations smoother and easier to understand. The frequency of how often we get feedback on our design went from once a week per milestone to now anytime we want.
Now looking at how our other TVD clusters look at the end, we can see that our two biggest target exceedances in the substructure and shell are compensated for in savings on services and specialty construction, thanks to our team's efforts. Now, to zoom in on one of the agents who has stolen the show when testing the tool with our team, it is the iInsights agent who observes the process when we run a design iteration through the system and remembers it for later. This becomes very powerful as it compounds over time, where the agent's knowledge base gets bigger and bigger. Now we have essentially an AI assistant that can expertly remember everything there is to know about our design.
We tested how accurate and reliable this agent's knowledge of our system is, and we were blown away by the level of detail with which it knows our entire design evolution. We were interested to know how the green roof has impacted our design and targets, and we were very surprised by the insights it was able to give us about our own design. Based on its internal knowledge, this agent can create detailed answers in the style of a report, helping us understand and track decisions, and it can also cater its answers to our domain of expertise.
Another aspect of our system, which is really powerful is the fact that this agent's memory stored in a vector database can be backed up, duplicated, and even given to other agents or systems to use. So for one, this could transform how we keep knowledge throughout a project and across projects, thus reducing fragmentation and lost knowledge in the industry. Another implication is that we can give another agent access to these memories. To exemplify this, we implemented a bot on Discord and we gave it access to the memory of the Insights agent to act as a light version of the system that can scan for the latest message on our channel and send an answer to our questions at any time. And we also saw an opportunity to make pool planning more accessible and enhance it with AI. So we built Pacific Bot, which is an AI-powered bot in Discord that answers questions about our pool plan in real time. We were able to create this by exporting the data from Nyali, which we processed to create a query system where we can ask this AI-powered bot questions directly in Discord, giving us access to the pool plan from our phones.
Now let's talk about how we plan to build this thing. We've designed a deeply collaborative, data-driven, and sustainability-forward construction workflow. It begins with aligning an optimal building placement using BIM 360 with the collaboration with architects. Next, we co-create a modular kit of parts with BIM and COPE AI. After that, we forecasted our running costs with LCFM through our TVD tool and the AI agent system. After that, we plan to track our materials in real time using Manufacton and our newly designed and proposed iSupply dashboard. On site, we have used Fuser as well as Alice and VR for traffic logistics simulations and serving an educational purpose. We optimized our schedule using Alice and minimized our site footprint using electrical equipment and robotics. Together, this creates an integrated, intelligent, and impactful system.
Starting out our exploration of prefab options with COPE, we fitted Latticube interior partitions to our building, since their ability to be demounted aligns very strongly with our team's desire for flexible spaces. This is when we realized our team's efforts to keep large floor-to-ceiling heights would not allow this, as 10-foot partitions is the tallest they produce. The design team noted that acoustic privacy would be a concern if we leave this gap, and filling it with some other material might also defeat the purpose of being easily demountable. Therefore, we used COPE's internal partition benchmark to fit standard light gauge steel and drywall partitions. We used optimization to minimize the number of panel types and non-buildable panels, using panel dimensions as the variables. Running through 40 iterations, we landed at 74 panels of 41 different types, all of which were sent back to Revit. We also decided to use COPE for fitting the geometry of our exterior glazed panels. We started out in Revit, where the curtain walls are modeled as a single element, and we brought them into COPE, where we used an existing product library which had similar dimensions to the architect's intended panel size. Then we fitted these panels, landing at 162 panels with 16 unique dimensions. The panelized curtain walls were then sent back to Revit.
Our traffic analysis showed that most of the traffic came from Lake Merced Boulevard on the west, and peak traffic flow was from 3 to 6 p.m., making us use the north and southern roads for entry and exit points for our site, and use a 7 a.m. to 3 p.m. workday schedule on weekdays. We're using local suppliers for low-carbon concrete, prefab steel, and MEP elements, all based out of SF for local just-in-time deliveries. We're using an all-star equipment cast, using all electric and robotics to reduce rework and increase efficiency. Having an on-site EV charging and renewables energy system will allow us to boost sustainability and also allow us additional incentive of up to $100,000 from SF utilities. We used Alice to optimize our construction schedule. With the use of built robotics attachment, we found a significant reduction in substructures, which is our bottleneck. Next, the race was to complete the shell as quickly as possible to minimize emissions and noise, which Alice proposed be done by starting exterior walls while the next floor frame is going up. Finally, finishing details are done using robots, and with all the scenarios that we ran that you can see on the screen, we found that equipment and crews with robots and a regular work week with a 7 to 3 p.m. work hours was our optimum schedule, which allow us a duration of 41 weeks.
After having prepared all these components in code for our kit of parts and scheduled from Alice, we can now add them to the rest of our kit of parts and move on to track the production and shipping to the site using Manufacton.
Our site logistics plan came after multiple iterations. A north-south internal road with a southern internal road allowed us to ensure smooth in and out movement of equipment deliveries without having to disturb the entire site. So it can go to the 2 designated laydown areas that you can see, as well as trash collection. This also allows us to separate the office and rest area from the busy construction site area. EV charging station near storage and equipment parking is also placed optimally on the site. We partnered with Recology San Francisco to track and log construction waste in real time, helping us divert materials away from landfills and recycle up to 70% of our site waste by using a QR code tracking system. We started with a base estimate of 240 tons of construction waste. By reducing our site footprint by 30%, we brought that down to 170. Next, incorporating prefabrication further cut it down to 100 tons, a 58% overall reduction from the original estimate. Throughout our partnership, we were able to divert or recycle with our projections from Recology 69 tons of waste, with only 25 to 30 tons of waste being projected to be sent to landfills. It's a smart, measurable, and mission-driven system, helping us build more efficiently while supporting SF's zero waste goals. Phase 1 of the construction is about excavation. Using our built robotics attachment on the excavator, we reduce crew on site for this phase, and the laydown area is used for shoring. During the second phase, we use just-in-time delivery of steel frame elements and a mobile truck crane to assemble it. As the slab of one floor goes up, the frame for the next floor is starting. As you can see, the truck crane is easily able to reach the entire height of the structure. Phases 3 and 4 is about shell completion and then the interior finishing placements. The picture is a representation on the right of Dusty making a layout and inspected, easily maneuverable and fits inside.
After discussing with LCFM, we decided to implement sensors for structural health monitoring, recording ground motions, structural element deformations, and building inclines. Also, considering MEP needs and the construction environmental impacts, we also want to install sensors for indoor temperature, construction emission, and noise.
As part of our rework reduction approach for the tech challenge, we propose integrating all media captured on site and use it for creating point cloud reconstructions of the as-built state on site, contributing to tracking construction process, and then with a QR code system, building upon the existing functionality of Manufacton, we can integrate all this information into the shipping orders to ensure drivers have all the information needed to deliver materials directly to the correct pick point on the site, reducing the need of rework that comes with deliveries to the wrong spot.
We came up with an idea to consolidate all this information and all the methods we are thinking of implementing for our workflow. So here's a visualization. Welcome to the iSupply dashboard, our idea for a real-time window into site operations, supply chain logistics, and environmental performance. Here, we will track the full movement of prefabricated materials linked with QR codes and Manufacton, directing deliveries on site. We want this dashboard to go far beyond the materials. It also syncs with the emissions and noise sensors on site and monitors the energy use across electrical equipment and EV charging station. This will give us a live picture of what's going on site. You'll also see data on the number of construction robots operating. Since we're partnering with Recology, this will also show the QR code information from Manufacton and Recology. And as for our students, as you see right now, the dashboard will have a dedicated student info zone powered by the iInsight bot. That's our prediction. It lets students ask questions, explore the design decision, and understand how the site operates. No information or outputs are going to waste. Together, the system is about visibility, accountability, and turning our job site into a living classroom for the future of smart, sustainable construction.
Now we're moving on to sustainability and finances, and we start with the energy system. And originally, we planned here to generate our own power using PV panels and wind turbines. But after running the numbers, we saw that by 2030, San Francisco will supply 100% green grid power, and that completely changed our approach. Switching to the grid allowed us to reduce CO2 emissions by 86%, lower our lifecycle energy costs by 25%, and most importantly, freed up the entire roof for our unique green design concept.
And by implementing energy efficient solutions and optimizing heat and light gains, we managed to reduce energy consumption by 74%. Since the building relies on purchased electricity, this reduction brings up not only environmental, but also significant economic benefits.
As California faces increasing challenges through drought, we knew that water efficiency had to be a priority for us. Therefore, we developed a low consumption system tailored to that need. And as you can see here, we managed to cut water usage by 68% compared to a standard setup.
In a region facing frequent droughts, a green roof might seem like an irrational choice. But with our iWater system, we created a closed water loop using purple water, which fully covers the irrigation demand without using any additional fresh water. And to make the impact of our sustainability measures more tangible, especially in terms of CO2 emissions, we wanted to explore the potential financial value. That's why we ran a calculation based on a future carbon pricing. California plans to include the building sector in its emission trading system for 2029. This projection helps us to show that our emission reductions don't benefit the environment only. They could also contribute to the building's economic performance over the time.
And now, to give our sustainability efforts a measurable benchmark, we pursued LEED certification and went through the entire scorecard. We achieved 86 out of 110 points, so enough to reach LEED Platinum. That not only certifies our environmental performance, but also adds long-term value. Studies have shown that with LEED certification, the property value can increase by up to 7%, making it a smart move both ecologically and financially. And to address the topic of risk, we conducted a sensitivity analysis for our key financial variables. We evaluated how changes in interest rate, construction costs, operational expenditures, and additional income would affect our IRR, which is our central performance indicator. And based on that, we created a best and worst case scenario. The result is, even in the worst case, our project remains profitable, and in the best case, we see a strong upside potential. And to manage those risks, we implemented specific measures. We fixed the interest rate for 15 years. We used a conservative forecast for additional income and added a 2% risk buffer to strengthen our resilience. And now we're moving on to our lifecycle costs. And over the full 25-year project span, our total lifecycle costs amount to roughly $42 million. This includes construction, operational and capital expenditures, and a category labeled here as specialties, which covers specific items like certification costs or the cleaning robots. On top of that, we also calculated roughly $14 million in interest, which is not part of the LCC, but still crucial for the overall financial picture. And now let's take a closer look at operation and maintenance. And thanks to a number of targeted measures, we managed to significantly reduce our operational expenses over the 25-year period. Key drivers here were our robotic cleaning system and the self-cleaning windows, and additionally, our efficient water and energy systems helped reduce utilities, and with our battery storage, we can purchase electricity during off-peak hours, store it, and rely on it when external prices are high. On this slide, we're looking at our income and net cash flow during the 24-year operation phase. In addition to our rental income, we've created additional income streams through urban farming, a cafe space, and the rental of our auditorium and large classroom. Together, the additional income adds up to around $125,000 per year. As shown by the yellow line here on the graph, our cash flow remains positive throughout the entire period, underlining the long-term financial stability of our project. So the next logical question is, when does our project actually start paying back? We reach our break-even point in the year 2049, and from then on, the building generates a financial surplus year over year. This marks a major milestone in the project's financial trajectory. And now, to sum it up, our project stands on a solid financial ground. We've achieved a strong IRR of 9.2%, exceeding the 7% benchmark. Key cover ratios like debt service and loan life remain consistently above the required thresholds, confirming our financial resilience over the 25 years. And altogether, this reflects a financially viable and future-proof investment. But of course, alongside our financial targets, we set ourselves ambitious sustainability goals. And because achieving strong financial results was only half the mission. The next step is about our sustainability targets.
The sustainability targets were measured using the sustainable target value tool. With that, we were able to continuously track the environmental performance of our building through the design process. This helped us to make informed decisions and stay aligned with our sustainability goals. Water usage was our most challenging target, but thanks to the implemented solutions and the support of AI agents in the later stages, which accelerated the data feedback, we were ultimately able to meet all three targets.
So according to our goals for the IPD challenge, we evaluate team mindset development by tracking KPIs. For interdisciplinary collaboration, more decisions are made between the design and financial teams so that the silos are broken. For asynchronous coordination, more pre-plan tasks are completed on time and more check-ins on pre-plan. Also, more stand-ups and pre-plans are done and more reports from the inside agents so that the cross-disciplinary progress is more visible to every team member. Moreover, less design feedback latency and less handovers between systems are achieved for streamlined communication for decision-making. Of course, it would be much harder for us to achieve those goals without the inside agent and the Pacific bot.
To wrap up, let's look at how we predict our proposed iSupply dashboard and how it can drive real impact. It consolidates all our information in one place and shows we have reduced on-site storage needs by 30% thanks to precise deliveries and better logistics. We can cut knowledge loss by at least 50% by capturing and integrating site data and keeping it accessible for engineers and students alike. And we've reduced construction waste by 70% through improved tracking, smarter prefab logistics, and our approach to maximize reuse and recycling. These KPIs show that we are not just cutting waste, we're building smarter, more sustainable, and more efficient projects. And that is the power of an integrated, intelligent supply chain.
To wrap up our sustainable challenge, from the very beginning, we knew this project had to be more than just a building. We aimed to bring together the economic, ecological, and the social dimensions of sustainability, not as a separate goals, but as a one shared responsibility. By connecting the dots through a sustainable intelligent chain, reducing environmental impact during construction, implementing systems that lower water and energy usage, creation of the space that works for the users, and zones that give back to the environment, we designed a building that doesn't just stand in response to Code Red for humanity, it acts on it from now.
Before we wrap up, here's what we learned about the project, the process, and each other. Some takeaways are thoughtful and some are silly, but together they tell a story of how we grew as a team, learning, failing, laughing, and figuring it out all along the way. And with that being said, we would like to thank all of the owners, mentors, and coaches who guided us and were with us on this journey. Thank you.